Okay, I would like to go back to where we were before the birthday book, the math models. Actually, before we talk about math models, we were right in the middle of the inheritance. I would like to finish, hopefully today, about all you have to know about inheritance, and possibly a small part on Wednesday, because we're going to talk about a few design patterns that's going to rely heavily on the inheritance. So I think it's quite important, even though many of the stuff you have learned already in 2030. But I think it wouldn't hurt to review a little bit. Okay? So what we're going to do is we're going to go back to our students example, okay, about resident student versus non-resident students. I might go a little bit fast today, but if you got any question, please just interrupt me if there's any part you don't really get. Okay? Okay, let me just talk about quickly the syntax for inheritance. Something you want to pay attention to, which we'll see quite a lot today. So in Java, whenever you try to declare some reference variable, let's say we got students over here, and the right-hand side, this can be a different class name, right? Okay, we call this the dynamic type. Dynamic, which means it might change as you go through your code. And once you declare this particular variable, it's fixed. So it's a static type. Okay, it's a very fixed concept for OOP. So now, how do we do the same declaration and creation in IFO? Let me just review that very quickly. In IFO, this is how you declare some static type. I can simply say S, and then colon, and then static type. And then, how do you assign the dynamic type? So you can think about what you do in new, in Java. It's kind of corresponding to a create statements in IFO. In this case, we say we're going to create an object and attach that or assign that to S, and the dynamic type is simply just going to be students. On the other hand, in this case, the dynamic type is simply resident students. Okay, that's something maybe you have picked up already. One small shorthand you might want to use. Let's say for this particular example here, you can see for S over here, the static type is simply students. And then we say that we want to assign the dynamic type to the same variable to be student as well. When the static and dynamic types are the same, you can omit that particular declaration. You can simply create s.make. Okay, so now whenever you got this, something without the brackets over here, this simply means the dynamic type of S is the same as, the same as the static type. Okay, something about syntax. We'll go into details about static type versus dynamic type. I'll give you some intuition first, and then we're going to talk about static type versus dynamic type. We're going to talk about casting, and also we're going to talk about how you can apply inheritance in the case of feature arguments and also return values. So these are the things I would like to go through quickly as a review, and then we apply them in the design patterns, which we're going to talk about. Okay? Any question about the syntax quickly? Are we okay? You might need them in the lab test. You may or may not. Okay? Make sure you are comfortable with those. Okay, so now let's go back to where we were. So I would like to use this as a quick review of the classes that we talked about before the math model. Okay? Again, if you try to recall what we said for this example here, we have a superclass or a parent class called students. Whereas in the student class, we declare name and courses and also register and tuition. Right? So these are the features we have. And they will be inherited to all the descendant classes, all the subclasses. In this case, we got resident students, and also we got non-resident students. Okay? Basically, every time you create inheritance, it's got to be that you want to share some code from the parents. And also, you also have the freedom to either define new features or to redefine existing features that you inherit. Okay? There are two possibilities. For example, you can see over here, premium rates and set premium rates. So these are the new features that are specific to resident students. On the other hand, discount rate and also set discount rate. So these are the new features that are specific to non-resident students. They don't exist in the parent class. On the other hand, you can see here, we got tuition over here, and also we got tuition here. We also have tuition in the student class. Basically, the way you calculate the tuition is simply just to calculate the base amount If you can just recall, just go back to the code for student class. And then, in the case of the resident student, we're simply trying to redefine that a little bit to say, not only that I'm going to use the base amount calculation, also I'm going to apply the premium rates to calculate the tuition for resident students. Similarly, in the case of the non-resident students, the way I calculate the tuition is also going to be redefined. Not only that I'm going to use the base amount calculation inherited from the parents, but also I'm going to use the discount rate to calculate that, right? So that's something we talked about in the previous lecture. Okay? If you forgot about details, please refer to the code in the slides. Okay, that's a very quick reminder about the classes and features we have. Now, let me just go to the number one important thing for you, okay? So now, let's think about some decorations and object creations. And I want to give you intuition right away, okay? Let's say over here, we declare S1, S2, S3, okay? They are of static type student. Okay, I will just come to the static type in just a moment. And also we got RS, which is of type resident students. We got NRS for non-resident students. Okay, and then over here we got a few creations over here, which means, for example, you can see in the case where, let me just give you one example here. Let's say for RS. RS, the static type is resident students. And also here we say RS, the dynamic type is resident students, which means they're the same. Okay, for example. Are we okay so far? Okay, let me dive into the point right away. What's really the use for static type? The way I put it, it defines expectation. Okay, let me write it down. Whenever we talk about static type, we talk about expectation. Okay, so static type, I'll put it here. Make sure you can see that. Okay, whenever we talk about static type, it's about expectation. Expectation in the sense that if I give you some object O in general, of course you can look up the declaration for object O and see what the static type is. As soon as you see the static type for object O, you can know exactly what you can put after O. You know that whenever you say O dot, if you do that in iPhone Studio, it's going to pop up a list of features you may call. Those are the expectations. Okay? The static type for each object is going to determine the set of features you can call. We'll illustrate that in just a moment. On the other hand, whenever you talk about dynamic type, okay, it's something different. Rather than expectation, it's about versions. Like which versions of the expected feature will be called. We'll get to dynamic typing a little bit later. Okay, so now let's do some exercise very quickly. Okay, but I think that's very important to understand. So now I want to ask you the following. So let's say S1. Okay, let me just do a little bit better. So S1 over here, you can see S1 was declared to be students. And then we also say creates students S1 that make. So that means that the static type of student is students. Sorry, the static type for S1 is students. Dynamic type just happens to be the same. Here's my question. I want you to tell me either check or cross, right? If I put a check over here, that simply means if I try to write S1.name, it is going to compile. Okay? If you don't think that should compile, it should be a red cross. Okay? Clear? Now, S1.name, should it be a check? Why? How about we just go through the row first and then you tell me why. What about S1.courses? Green check? Okay. S1. Reg over here simply means register. Okay, just a shorthand. What about S1.register? Check. Okay. S1.tuition. Okay, very good. S1.premium rates. I heard yes. That's good. So somebody is so confused. That's why having this lecture is good. Okay. Who said yes? Who said yes? Nobody? Oh yeah. Was it you? No, it wasn't you. Okay, that's fine. Yeah. Okay, good. Okay, the reason is, okay, so this one here should be a cross. The reason is simple. When we talk about something compiles or not, only look at the static type for expectation. So here, when you have, let's say, S1.premium rates, all you got to do is to go to the variable over here and see what the static type is. In this case, students. Students is the static type. And then you want to see if the feature you're trying to call is part of its expectation. Basically, you want to see if PR, premium rate, is declared in that particular class. Is premium rate declared in this particular class? No, it's declared only in the subclass. That is why it should be cross. What about set premium rates? Also no, right? Okay, hopefully you can see discount rate, and set discount rate also is not good. Okay, are we good? Are we good? Okay, let me find a tricky one for you. Oh, actually S2 will be tricky. Okay, what about S2? Let's now talk about S2. I'm going to use a different color here, orange. S2 was also declared to be static type students. And then we are trying to say creates resident students S2. That means S2, statically speaking, is a student object. However, dynamically, it's pointing to a resident students object. Okay? So now, let's try. S2.name. Good, thank you. S2.courses. Good. S2.register. Check. S2.tuition. So far, so good. Good. S2.premium rates. Let me give you a little bit hints. S2 is actually pointing to a resident students. So should it be check? You think so? How many of you don't think that's the case? Oh, actually quite many. That's good. So my hint was misleading intentionally. That's not right. Okay? It's a very common misconception. When you talk about whether things should compile or not, you don't care what the dynamic type is. Even though, okay, thinking this way, if you look at this line here, okay, let me draw a very simple diagram here. Basically, we have S2 is pointing to some objects over here, which is resident students. And S2 itself was declared to be a student. Okay? So basically, this is the static type, and this is the dynamic type. Whenever you talk about expectation, the dynamic type is simply not relevant. Only the static type is important. So that is why, in this case, it will just be cross. Okay, and also cross, cross, and cross. Because S2 was simply declared to be a student class. So that means everything you can expect on S2 will just be what you can expect on the students, even though S2 is pointing to a resident student objects. In this case, if you're so sure S2 is really pointing to a resident students, which got premium rates, one thing you can do, cast. Okay? That's something we'll get into. Okay? It's actually a quite related story. Yes?
Question. What if at runtime I want to do something like what class is this, or what?
You mean like what instance this is, right?
Yeah.
We can do a cast. Yes, you have seen that already in so far. It's called attached. Okay, let me just, since you asked me, so let me just say very quickly. In Java, you would say, for example, if object O instance of some class C. In that case, you can do something here, right? You can do a cast. In IFO, you got something corresponding to it, okay? In IFO, actually, you know the syntax already. You would say if, let's say, attached, which is a keyword, class C, O. And then you can do something here. Okay, just the syntax, okay? Okay, I'm good. Now, let's do one more. Yes, go ahead.
What would it be? Would it be the dynamic or the static type?
Okay, good question. Whenever you do casting, that means you're temporarily creating a variable that has a different static type. We'll get to it. Yeah, but for dynamic type, when you want to change dynamic type, you don't do it by using a cast. You only try to do it using a reassignment. Okay, yeah, we'll get there. Get it. Good. Oh, by the way, everything we talk about today will be relevant because later on when we talk about visitor, when we talk about composite, when we talk about observer, state pattern, they all have to use this kind of concept. That's why it's really important, okay? I may not finish today, but definitely on Wednesday, and then we move on to design patterns. Okay, good. So now let's, okay, are you okay with this table here? Okay, good. So if you look at the slides, okay, that's the syntax we just talked about, and that's kind of the table, like that. Okay, you can review the table, make sure you have that intuition. Again, When we talk about compile or not, expectation, and only look at the static type. Okay? Having that intuition in mind, let's have a look at some example further. I want you to, again, build some intuition about polymorphism versus dynamic binding. So in this slide, we do polymorphism. Okay? So now, we know that, let me just remind you very quickly. We know that students over here is a superclass, and resident student is a subclass, okay? Having that in mind, can we have a look at this fragment of code over here? Let me remind you very quickly. I'll draw it aside. So we have students over here being the superclass, and also we have resident students being the subclass, okay? Good. Okay, let's say we declare S1, we declare S and RS with static types, and also we try to create these two lines, okay? Create different dynamic types. And now, my question for you, of course, also you try to set out the premium rates. Line number 8 and line number 9. I'm pretty sure based on what you learned in 2030, you know which one should compile, which one shouldn't. Let's answer that question first. That's something I assume you know. But what I really care more is whether or not you can explain one should compile, but the other one should not. And this has something to do with expectation. Okay, let's do one by one. There are two questions over here. Question number 1. Line number 8 and line number 9. Which one compiles and which one does not? If you do believe both should compile or both should not compile, you can also say it out. That's fine. Anyone? Line number 8 compiles and line number 9 does it not compile? Okay. Anyone who got a different opinion? Okay, good. I agree. That's good. That's what you learned from 2030. So this is good, this is not good. Now, can anybody explain to me why? Especially, let's focus on line number 9. Why would line number 9 not compile? Can anybody explain to me?
Something to do with like voting, like line number 9, if you're assigning RS as grade to a student, but like.
Yeah, I see what you mean. When you say promoting or downgrading, yes, but it's a little bit vague. Mm-hmm. Yeah. Can you, for example, let's say you want to prove this. Can you give me a scenario where having, let's say this, you learn about proof by contradiction, right, in math. If you believe line number 9 should not compile, why don't we temporarily assume it did compile? And then it might lead to something that's disastrous. That would mean our original assumption is wrong. Okay? But you want to say something, go ahead.
You don't know that S is going to have all the functionality that resident students have.
Premium rates, yes.
So if we assume when we assign RS about premium rates.
Absolutely, absolutely. That's exactly correct. That's exactly correct. That's why I talked about expectation in the previous slide to get you prepared. Okay? It's all about expectation. Let me write it down properly for you, okay? It's also on the slide. It's really important to get this through. You will see this concept over and over again, not just in a simple assignment. When you try to pass a feature argument for feature call, or when you try to reassign some return value to some variable, everything applies, okay? Line number 9. That's the line I want to focus on very quickly, okay? Let's say we say this. Assume, just for now, RS is assigned to S compiled. Let's just assume that. If that compile, what's going to happen? Let me draw some diagram to show you. That means over here, we basically have, originally, let's say over here, from this line, we have students, and then we have S pointing to it. And student is basically Stella. Okay, and then from this line here, we also got RS is pointing to another students over here, which is of type resident students. And then it's Rachel. And what's more, for resident students, we also can set RS to be of premium rates 1.25. I'll put it here. Basically, premium rates is 1.25, right? So now, our assumption is this particular reassignment will be valid. So that means we can do the following. RS, rather than pointing to this current object over here, it is going to be reassigned to point to this particular objects, right? That's what we are seeing. So now, we want to give a counterexample which shows this assumption is wrong. Why? As we learned from the previous slide over here, whenever you have a static type, all you can know is about the expectation for that particular variable, right? So now what I want you to tell me is, what's the expectation? That's step number one. Step number two. Expectations on RS. Anyone tell me what's the expectation? Just have a look at over here. Okay, look at the hierarchy here. What are the expectations for RS? Okay, basically you got name, you got courses, all the features in student class, and also all the features in non-resident student class. Does it include, sorry, let me say it again. All the features in students and also all the features in resident students. Does it include discount rate? It does not, right? Okay, very good. So let me write it down. You got name, you got courses, you got register, you got tuition, and also you got premium rates. You also got set premium rates. So these are the expectations on RS simply because it was declared to be the case statically. So now, since those are expectations, that means if you try to write something like this, number three, based on the expectation we learned from static type, okay, it's based on the static type. If I try to say RS dot, for example, premium rates, is it going to compile? Compile. So you know that there are two timings, right? One is compile time, the other one is runtime. Right? Compile time, of course, you can get compile time errors if you got either syntax error or type errors, right? Which means your code cannot be even executed. You've got runtime error, which is more often the case. You got compilable code, but you run into some exception or logical error in the runtime, right? So different categories. So now in this case, if I say rs.premium rates, would it compile? Why would it compile? Because the static type is there, right? Okay. So now let me write it down. It compiles because the static type of RS, which is resident students, declares that. It compiles. But now, what if we execute it? Since it compiles, so we can execute the code. It compiles. Runtime. What's going to happen? Well, the thing is, since I say I can execute it, so that means I'm going to say rs dot PR. So I'm basically following the memory address for rs, go to this object here, I'm looking for a PR. There's no PR. Crash. It's going to be a runtime exception or runtime assertion error. Okay? Crash because the student objects does not have the premium rates. That's a problem. So, okay, let me just finish this and then I'll take your question. So now, our original assumption there, saying that this should compile, will lead to crashing scenario there at the runtime. So that means our original assumption was wrong. So the opposite should be true. So that means number 4, RS is assigned to S, should not compile in the first place. Okay, that's the whole story. Okay, it's a very important intuition for you to get. Okay, we're going to see lots of instances like this. But questions? You mean number 3? Why it okay. Whenever you talk about if a line compiles or not, you always talk about expectation, right? Expectation comes from static type only. So when you look at this particular feature call over here, you want to see what's the static type for the target, for the context objects. In this case, we know that the static type is simply declared over here, resident students. So now we want to see whether or not PR, the premium rates, was declared in the resident students. If it is declared there, that means it's part of its expectation. If it is not, then it's not.
So at the end, would you say that R is supposed to address this runtime error?
I'm saying that, okay, so this one here, overall, will be a compile time error. Okay, so that's why I put a cross mark here. It doesn't compile. The reason, the way I judged it, the way I justified to say that should be a compile time error was by saying, if you allow that to happen in the compile time, it will lead to some runtime crash, which we want to avoid. That's why it would have been a compile time error in the first place. Okay. Because having compile time error is much cheaper than having a runtime error. Think about, would you rather find out there's any software defects in your airplane before it tried to take off or after it's taken off, right? You definitely want to find all the errors before it's taken off, right? Guys, are we okay with this? Okay, we're gonna see lots of applications of this, okay? So if you're okay with this, I'm gonna move on. So this guy over here basically just tells you about polymorphism, okay? Basically, let me say one more thing. Whenever you say, let's say, so that means this guy here, S is assigned to RS compiles. Okay, there's another term I would like to mention quickly. Okay, whenever you're trying to say this is assigned to something else, okay, there's one way to say it. That means we want to substitute RS, which is the right-hand side, for S. Basically, when you are expecting a student, can we substitute it by a resident student? The answer is yes. So that's why the assignment should compile. Okay? Okay. It's called the substitution principle, but we'll see that in the slides. Okay? Let's move on to the second concept. Okay? So polymorphism basically means whenever you want to have some assignments to substitute one variable for the other, you want to talk about expectation, right? If the expectation can support, then it compiles. If it cannot support, it does not compile. Okay? Good. All right. The second one is about dynamic binding, okay, which we'll see also very often later. Okay, so now I already have some diagram over here to show you, but let's go on very quickly. Okay, so basically we have, again, we have over here C is a type course, S over here is students, right? Oh, think about another thing. When I say S is assigned to something over here, which we'll talk about a little bit later. We know that S over here, the static type is simply students. So now, in general, what can we assign over here? Question mark. Basically, you want to assign any variable whose expectation is simply at least as many as the original S over here. Okay, that's something we'll go into. Okay. Again, everything is about expectation. Okay, but now for this particular case, let's see what's going to happen. So what we have is, so we want to create a course object over here, 3311, let's say 100 over here. Let's say we got RS, and then it's pointing to some, oh, sorry, not here. So we have a course object over here, and then, oh, let's say C. C is pointing to this course object here. 3311, 100. That's easy. And then we also have two objects over here. The first one is going to be RS, the second one NRS. Okay, so RS is pointing to some resident students objects, and NRS is pointing to non-resident students object with the name, courses, and the rates. Okay, so far so good. Okay, so now let's try to see this. Okay, of course you can also set a premium rate, you can set a discount rate. Okay, you can also do register if you like. Okay, so now I want to look at line number 7 first of all. Okay, so now as we talked previously in the previous slides, this will compile, right? Because whatever we expect on the static type for S, which is students, they can all be supported by the static type for resident students, which is just for RS, which is resident students. Okay, so if this compiles, that means S is going to point to this particular object. Okay, so now question for you. If I say S.tuition, how is the calculation going to be like? Remember, we actually got 3 versions of the tuition. Let me show you over here. Right? If you look at the 3 classes we have, we got tuition in the student class. We got tuition for resident students, we also get tuition for non-resident students. 3 versions. Okay? So now, it seems to be sensible in the following way. You know what? Let me just try to see if I can copy this diagram over here, and then try to, oh, that's too big. Actually, never mind. Okay. Let me just go to here. So now, let me just ask you this. So we have students. So we have resident students, and we have non-resident students, right? In the student class, we do have tuition. In the resident student class, we define tuition to be something else, depending on the premium rates. And also in the non-resident student, we also got tuition. We define to calculate based on the discount rate. Okay, we got 3 versions over here. Now, my question is like this. When I call this particular line over here, which version am I calling? And my hints to you. The static type of S is students. So which version? Version 1, version 2, version 3. By the way, my hints may or may not be misleading, right? Okay. So which version would we call? Version 1, 2, or 3? 2, good, exactly, okay? It wouldn't be 1. So for the, a common misconception would be, you look at the static type for S, which is students, and you'll simply say, I'll call the student class tuition. That's not right. Whenever you talk about which version at the runtime to be called, it's about dynamic type, okay? So now in this case, it's gonna be this version over here. So it's going to apply the premium rates. If you do the math calculation, it's going to be 100 over here multiplied by premium rate, which will be 125, right? Okay, let's see what's going to be more interesting in this. I'm going to have exactly the same line after that, S dot tuition. However, before I do the S dot tuition, the same identical line, I'm just going to do another reassignment over here. S, the same variable, is reassigned to NRS. We know that should be allowed. Rather than pointing to over here, it's going to point to this particular object, right? That's a real. So basically, whenever you're changing the objects over here, changing from this particular object to this particular object, you're modifying the dynamic type. Static type always the same, always. Okay. So now, question again. S dot tuition, as we know previously, at this point, is going to call version number 2. What about now? Version number 2 still, or version number 1? 3, good. Good. All right. It's going to be version number 3 simply because currently it is pointing to this, which means its dynamic type is non-resident students. Are we okay with this? What you will see in the later design patterns, things will just be a little bit more complicated in the following sense. Rather than considering just a single variable, we're going to consider a collection. If you have an array of students, for example, right? I'll just give you a little preview, but we're going to see that. If I have an array of students, okay? Basically, you can think about each slot is like a single variable, right? And now, if the array somehow is declared to be of student type, okay, you can say array of type students. So that means every element over here is expecting a students. If we are expecting a students, what can be the actual dynamic type? It can be either resident students or non-resident students. So that means the actual type over here that's being pointed to can be different. That's something we'll get into. It's called polymorphic collection, which we'll see a lot for every design pattern. Okay, good. Guys, are we okay so far? Good. Hopefully you find it easy. So we only have to bother you for 1 lecture or 1.5. Okay. Okay, that's good. But all the detail analysis is on the slide. You can go over them. Okay. What I want to do now is to, okay, also again, the intuition for dynamic binding. I want to go over just a little bit more points over here. And of course, in general, you may want to have a multi-level inheritance. That's maybe something you want to do for your projects. Okay? Maybe for your lab number 4, you don't really need a multi-level inheritance. You don't necessarily need it. But when your types of entity becomes more complicated, you might need this kind of architecture. Okay, that's something we'll try to do. Smartphone. Okay, I'm going to go over that when we get there. Okay. Okay, and over here, okay, it's just about data type. So what is really a data type? Data type can be integer, can be string, or can be some reference type. So whenever you talk about data type, it's basically a set of runtime values that are related. Now, in the context of inheritance, data type is particularly tricky because when you have an inheritance hierarchy to consider, the data type becomes flexible in some way. Okay, we'll get there. Okay, so every time when you're given a particular inheritance hierarchy, you basically form a way to actually build your data types. Okay, we'll see some example. Okay, so the root is always the any class, or in the Java case, it's always the object class. Okay, we're using inheritance. Okay, let me just, we do have some terminology here to introduce. I'll use some example. We got something called ancestor, we got something called descendants. Okay, let me just tell you right away. And then especially, I'm going to illustrate some point over here. When we talk about ancestor classes, we want to say every time when you have some descendant classes created, you always get wider range of expectations statically. That's something you really want to see why. Okay, you can read the slides, but I'm going to show one example to you. Okay, one should be enough. Okay, also we got another one. Let's say this one here is a little bit symbolic over here. Is that complicated enough? So now you can see that, let's see one by one. You can see the top of the hierarchy is simply A over here. So let's talk about A. Okay, so here is how I define ancestor and also descendants. Ancestor basically means all the parents of this particular class, including itself. Okay, in this case, it will just be just A. Okay, and then what's the expectation for A? And let me just tell you that we assume that at a class A, we simply declare AN, and then in class BN, DN, etc. Right? Let's talk about expectation. Okay, because that's going to decide whether a line is going to compile or not. What's going to be an expectation for A, just for this particular class? If A was declared as a static type, what would be the expectation? Just one, AN? Okay. What are the descendants for? Well, C, okay. Oh, actually I haven't introduced descendant, right? Descendant simply means all the children and the children of children and also go all the way down for the whole tree. Basically, yes, descendant. Well, you can see from the English word descendancy simply means not only just immediate children, but also children of children, and etc. Descendants basically all the classes. Okay, one thing I want to point to you. Because we talk about the root of the tree, this is the class with the minimum expectation. Because at this level here, I only got AM defined. But as I go down to the inheritance hierarchy, I will introduce wider expectation. Let's see. What about C over here? What's the ancestor for C? A, and also including itself, don't forget. Okay? Just for my particular definition, we include itself to be itself. So one class is both its ancestor and descendant at the same time. Okay? What would be the expectation for C? CM for sure. Because CM was declared here. Anything else? That was the inherited from here. You can see that so C is a descending class of A, and we got strictly more expectation. That's why we say as you go down the inheritance hierarchy, you're introducing wider range of expectation. What about the descendants? Very quickly. For F, G, H, J, and C, right? Okay. Itself, F, G, H, and J. Okay, you get it. So now, question for you. In this particular inheritance hierarchy, what are the classes with the most expectation? Huh? J, for example, J will be, right? Well, basically, the lower, it depends on the depth of the nodes. So J here, and also possibly I here as well, right? Because they are actually almost at the bottom there, right? Good. Are we okay with this? Good. Okay. I do have another table for you, but I think you pretty much get it. So we can get to some more interesting example. I'll leave that. So if you, when you review the notes, you can do that as an exercise if you're confused. Okay. So now, after talking about, okay, so this one here I already said when I talk about the student class. So one way to view inheritance is about accumulating the code, but you want to see more, you want to see something beyond that, which is what see beyond what you learn in 2030. So whenever you try to go down, whenever you try to go down the inheritance hierarchy, you actually introduce more features. That means you got more expectations. Sorry about that. Okay, so this slide over here, I'll simply just let you read it through. So because I also already talked about it. At descending classes, whenever you introduce it, you may try to either declare new features or you may want to redefine the existing features, right? So these are the two things you can do. Okay. One more thing to say. That is why whenever you talk about a particular descendant classes, they always have wider range of expectations. You just got more features to be called on a particular descending classes. Okay, we're going to see more example. Okay, are we okay? Good. And then here is simply just something about substitution, which whenever you do some assignments, you want to know whether the assignment will be valid to do. And the way to think about it is about expectation, right? That's something we also talk about in the intuition. For that one, I also leave it to you. Okay, just more reading here. And then what would be safe to do? Basically, this is the only rule you have to be very familiar with. Okay, whenever you have something like this. So every time, let me just tell you the number one rule you have to know. So whenever you have, let's say, object 1 is assigned to object 2, when does it compile? What is exactly the typing rule that Eclipse or iPhone Studio implements for you? Go ahead. Yes. Which one is the descendants? Okay, you're saying O1 should be a descendant of O2, well, O2 should be a descendant of O1. Okay, let me be more precise over here. Okay? Sorry? Yes. Basically, what you want to see is the static type of O2 is a descendant of the static type of O1. Okay? So you can think about the static type over here is the descendants, and the static type over here is the ancestor. Because the descendants has more expectation for you to expect, so you can substitute it without any problem, not the other way around. Okay, are we okay with this? Okay, good. So now, let's talk about cast. Okay, that's about rule of substitution. And then, so these slides are very easy, simply just tell you how you can declare variables and how you can change the dynamic type. They are very easy, so I don't need to go over that, but you can just review them for your study. Okay, what I would like to go directly into is the by the way, something I want you to look very quickly. Okay, you can see that. Let's say this. For example, when I say over here, Jim is assigned to RS over here, right? Let's just have a look at this very quickly. Okay. Now, question for you. If after this particular assignment over here, given this fragment of code, after this, what would be the static type for Jim? Static type. Student, right? Okay. Anyone else? Anyone want to argue a different answer? Basically, as soon as you declare Jim to be of static type students, it never modifies. It doesn't change. So even after Jim is reassigned to RS, it is still of static type students. On the other hand, after executing Jim to be assigned to RS, what would be the dynamic type? Right? How do you tell? Short answer is because we know that from this line over here, we know that RS is pointing to a resident student's objects dynamically, right? And then in this line over here, we're saying Jim is now going to point to wherever RS is pointing to. So Jim is also going to point to that resident student objects. So that's why Jim's dynamic type will become resident students. Okay? Does it sound easy for you to keep track of? It sounds easy. However, in general, to really keep track of dynamic types in your code, for those of you who took 2001 before, is an undecidable problem in the following sense. Okay? Let's say over here, okay? Because according to you, right, many of you actually knock your head saying, oh, that sounds to be very easy to keep track of what a dynamic type is for each variable. It sounds like. Now, let's consider this, okay? Let's see what's happening over here. So now I'm just trying to give you a move on a little bit more on the story, okay? Let's talk about these four lines over here. So now let's say this. Jim was declared to be a student object statically. And then we're saying that Jim is now going to point to a resident student's objects, which presumably we got name, of course, and we also got premium rates, right? Presumably, okay? Oh, of course, this is Jim Davis. And then what we try to do over here is we want to say, since Jim is really pointing to a resident student's objects, so we simply want to say, I want to say RS is assigned to this particular resident student objects. And then after that, I want to set a premium rate to be 1.5. It sounds intuitively acceptable. But is this fragment of code going to compile? Yes? No? If it is not going to compile, which line is not going to compile? Guys, please, wake up. Right? RS is set to Jim, okay? You're saying that that line shouldn't compile. Actually, we just talked about it, right? Because in this case, we know that Jim, whose static type is students, does not have as least many expectation as the static type of RS, which is over here, right? However, why is the compiler so inflexible? Because as you can see from here, we simply know that Jim is really pointing to a resident student objects. It should be quite easy to keep track of. So the compiler should really allow this. But in fact, compiler doesn't allow this. Okay? For your knowledge, I just want to say this very quickly. In general, let me just describe to you a program over here. Okay? Let's say this. Let's say if you can write to me a program that looks like this. Your program, okay? Which is going to take two things as input. One thing is any class, IFO class, C.E, okay? Or Java, doesn't matter. And then you're going to give me a variable x. Okay, so these are the two inputs for your program, okay? The output is very simple. You're going to tell me what is the last dynamic type of x in class C. For example, if I simply got something like this, I declare x to be of type students over here, and then I say creates resident students x dot make. Also, I have creates non-resident students, the same variable that make. If I actually pass this program over here to your program, what will be the output? What's the last dynamic type in this case? That's the non-resident student, right? That's the last one because that's the last line, right? Okay, so that means the answer here should be just NRS. Do you think you can write such a program? Did it seem intuitive to you, like how to write this program here? Oh, actually, by the way, C.E over here can be any arbitrary IFO program containing loops, recursion, if statements, and assignments, anything. Even it can be even an ETF project, right? Okay. Do you think it's doable or not? In fact, this is undecidable. Okay. For example, I just give you a very easy counter example. What if I give you the following? What if the program I simply give to you say something like this? From until false. Loop something here, end. And then I can, over here, I can say creates NRS x.make. By the way, for those of you who are a little bit uncomfortable, well, hopefully you're comfortable with writing loops over here. This is equivalent to when you say while true in Java. That's something we'll talk about when we talk about program verification. So now, for this particular fragment of code, what's the last dynamic type for x? There's no dynamic type because it never terminates. You don't even get to that point, right? Just one of the counter example I can give to you. That is why this particular program here is simply not decidable. This is why there's no compiler, for example, in Java or IFO that can actually keep track of what a dynamic type is. Okay? So now, let's come back to reality. If the compiler has this inherent problem about keeping track of the dynamic type, how can we overcome that as a programmer? If you're so sure my object at this point is really pointing to this particular type, you can do a cast. Okay? So that's why we are talking about cast. Yeah, this slide here is not exactly relevant to this course here. I want to draw some connection to 2001, right? I'm not sure if they talk about this problem here being undecidable for 2001. I guess not. Okay, so now all we can do is, if I really, really want this particular line to work, I want to tell the compiler, just trust me. Convert gen somehow to another kind of variable with a different static type. That's what I can do. Okay, let's see the syntax first, and then we'll go through some exercises for cast. Okay, so now over here, this is how you do the cast. Okay, let's see over here. Okay, overall we have check, then, and end. So this really not an explicit cast syntax for IFO per se, like in Java. I'm just trying to give you something that's kind of a like almost equivalent. Okay, but that's how you can do it when you want to do some cast. Okay. Basically, you're trying to write some check assertion. Basically, you want to check some expression there which might be either true or false. If the expression you're checking is simply true, you pass that. If it is false, you run into some check assertion violation. Okay, let's see that. So let's try to understand the syntax over here, right? So now, if you say attached, okay? When I say attach over here, attach is a keyword and then some class name. So this is more or less equivalent to when you say instance of resident students, pretty much like that, okay? To say gen instance of resident students. And now, what's really important is this particular line, this particular clause over here. Okay, let's just remind you the context again. So when I talk about gym, right? You can see from the previous code, gym was declared to be of static type students. Okay, I'll just put student beside gym. Okay, and gym is really pointing to some resident students objects. Okay. The only thing I can call on gym, the expectation, will be I can say gym.name, I can say gym.courses, However, when I say gym.premium rates, this is not allowed. Agree? Because if I look at the expectation for gym statically, gym is basically declared to be of type students. In the student class, you don't have the premium rates, even though you're pointing to a resident student objects. Okay? Now, if you really want this to happen, this is what you would do. Once you get this check syntax over here, in that case, because we know that attached resident students for gym is really being attached to a resident student objects. So what we can do now, what IFA would do at the runtime, pretty much like how you would do it in Java, do a cast, is going to create another variable over here. Okay, let me just use a different color. It's going to be rs gym. However, this particular variable is going to have a different static type. Okay? In this case, it's simply just going to be resident students. And then it's now going to point to this particular variable. So now, do we have more expectations on rs gym compared with gym, or do we have less expectation? In this case, more, right? Because we know that resident students is simply a subclass of students. So basically, whenever you're doing a cast, you're basically changing the expectation. You're modifying it. You're basically creating new variables with either more, in this case, expectation. You can also create new variable with less expectation. Okay, I'm gonna give you an example. Okay, but are we okay with this over here, right? So once that's what you will see over here, I can simply say rs does set premium rates because I can simply say rs gym is simply assigned, and then I can use that to call the set premium rates, right? So now, let me say one more, and then we'll see more example. Okay, we're gonna see how we do the cast. Okay, guys, are you alive? We are, right? Good. I am. I hope you are too. Okay. Now, when you talk about cast, so there are two kinds of cast you can do. Okay, you can either try to do an upward cast, or you can try to do a downward cast. Okay, in this case, we are having a downward cast simply because you can see for gym, its original static type is simply just students, and we are trying to cast that into resident students. In this case, we're going down on the class hierarchy, so that's downward casting. In the case of downward casting, we are basically allowing more expectation. Okay, symmetrically, you can also try to do downward casting. Whenever you're doing downward casting, you can also try to cast from maybe students into something that's up. But I will see another example. Okay, when you do downward, sorry, what I meant to say. Sorry about that. I just got my. I think that what I really meant to say over here, this is downward casting. You're allowing more expectation, right? And then for upward casting over here, you're actually restricting, and then you got less expectation. That's just the general principle. Now let's see examples, okay? I'm gonna show you. Now, let's have a look at this example over here, right? So now let's have a look at very quickly some example here. So let's say, so we just got a different example. Rather than students, we got smartphone, okay? So now let's see. So we have smartphone over here, okay? Under which we got either iOS, we got Android, okay? And then we got different models below, okay? So now let's see this. The minimum expectation we have on the smartphone, we got dial and also we got surf the web, okay? And then for the case of the iOS, you may try to redefine the surfing the web using some particular browser, for example, Safari. In the case of Android, you might do that using Firefox, right? And also in the case of the iOS, you might have some new feature called FaceTime. And for Android, you got some new feature called Skype, okay? Which means FaceTime is only available for iOS, but not Android. And And also Skype is only available, let's say, in Android but not iOS, okay, and etc. Okay. So now, are we okay with this? Okay, let's try over here. Let's go over the following fragment of code to see how you might do either upward casting or downward casting, and what the consequence is for each one of them. Okay. First of all, let's see. Let me just undo this so we got a cleaner picture here. Okay. So now let's say we declare my phone to be of type iOS. Okay. So now to keep track of that, iOS is over here. So this is the static type of my phone. Okay, so now when we do cast, okay, all right, let's create something first, okay? So now let's see this. Is this line going to compile? This line here. Think about it. What are we doing here? We're saying that iOS over here is declared a static type iOS over here, and now we are trying to give it a dynamic type. Let's say iPhone 6s Plus. Should it compile? It should, right? Okay. Basically, as long as the dynamic type is a descendant class of the static type, then we are fine. Okay. So now in this case, we have iPhone 6s Plus. Okay, so this is the dynamic type. Okay, now we're fine. Okay, so now let's talk about what you can call to make things compile. Okay, let's say immediately after, well, actually, you know what? The text I have over here, but it's kind of in gray out. So let's talk about it from scratch. Over here, if I simply give you my phone, what would be the expectation at this point? What can I call? According to the diagram here, I can make it a bit bigger for you. Yeah, I definitely can call dial. I can call surf web. Anything else? FaceTime, right? Good. Okay, so there'll be dial, there'll be surf web, and also I got FaceTime. Can I actually call, for example, 3D touch over here? No, right? Even though the dynamic type is iPhone 6s Plus, but as long as the static type doesn't support it, you cannot call. Okay? So that's why 3D touch over here and Skype, they don't work. Okay, that's about what the current state is. Now, I want to do some casting. Okay? I want to show you how flexible it is for you to do casting. You can either try to, okay, at the moment, these are the expectation for this particular variable of static type iOS. I can try to create different variants of this variable here with either more expectation or less expectation, either more or less. Okay? Let's see one case over here. So now let me just do one more thing over here. So from this particular line over here, from these two lines, we're basically saying my phone is now pointing to some basically iPhone 6s Plus objects over here. That's what we have. Okay? And then my iPhone over here is the static type is simply iOS. Okay? Let's see the first cast. The first cast. First of all, we want to know whether there's an upward cast or downward cast. Is it upward or downward? Downward? Are you sure? Well, basically you want to see which class it's trying to cast into, right? Yeah, this one here. Oh, this one here, right? Basically, you can see we're trying to cast that into smartphone. Smartphone is actually above the current static type. It's upward casting. Okay? So this is an upward casting over here. Okay, and then we're going to cast that into SP. Okay, what does that mean? That means we're creating a new variable SP over here. The static type is simply smartphone, static type. However, it's pointing to the same objects. Now, here's a question. After this cast, I can tell you the cast is valid. You can either do upward or downwards, either way. Okay? So now, what would be the expectation for SP compared with my phone? Same, less, or more? What's being taken out? FaceTime, good, thank you. So that means over here, the SP, the expectation will, because it's now smartphone, so we simply get only dial, and also we got surf web. Okay, even though they're pointing to the same objects. So the critical point for you to realize is, even though these two variables are pointing to the same objects, but because of their static type, the expectations are different. Okay? Let's do one more. Okay? What about over here? Now, are we doing upward casting or downward casting? Yes. Downward, right? Good, good, good. Because you can see we're trying to cast that into this particular class, which is below its static type. This is downward casting, right? Okay, good. So now in that case, and we're going to create basically just another variable here, which is going to call IP6S plus, pointing to the same variable. But now the static type for this particular variable is basically like a more specialized. So I'm going to put it here. iPhone 6S plus. So now, the expectation for this variable here, if you compare that with my phone, do we have more expectation or less expectation? More. Good. Strictly more. Give me that. What's the more expectation we have? 3D touch. Exactly. Good. So for now, for iPhone 6S Plus, basically everything you have as before. You got dial, you got surf web, you got FaceTime, and also you got 3D touch. Okay, that's kind of nice. Little example to show you how you can do upward casting or downward casting. Okay, one more thing to say about casting. It seems fun to actually do such upward and downward casting, right? However, if you are not careful, you might run into trouble for yourself. The reason that we want you to do casting is, for you as a programmer, you believe you know what you're doing. So you can force the compiler to believe this is the dynamic type. However, it could be wrong sometimes. In that case, you run into the runtime crash. Okay? So you got to take consequences. Let's see exactly how this can happen. Okay? Now, let's see exactly over here. So we got just a similar example. So let me just go straight to the point over here. Okay? Now, let's see this over here. Let me just use a highlighter here. Okay, first of all, let's start with my phone over here is simply Android. Okay, so this is the static type. This is the static type of mine. Okay, and then we also have over here the dynamic type. Okay, so which is Samsung over here. Okay, it's always important for you to see what the static type and dynamic types are. Okay, and then this is the dynamic type of mine. Okay, that's the context. Good. So now I can tell you that 1, 2, 3, and 4. All the 4 casts compile. For that to be compilable, you just want to know whether there's an upward casting or downward casting. Okay? Is this an upward casting? It is, right? You're trying to upward cast to smartphone, right? It is. And for Samsung over here, you're trying to do downward cast to Samsung, right? And over here for HTC, you're trying to do downward cast to HTC, right? That's also downward casting. And for this one here, it's also downward casting. You're actually downward casting 2 levels down. You're going to downward casting to Galaxy S6 Edge. Okay? Okay, without telling you exactly what the issue is over here, all the 4 typecasts over here compile. When you try to run them, are you going to have any crash? Yes. I heard yes, good. Otherwise, I wouldn't ask you that, right? I can tell you there will be at least 1 crash. How many crashes will we get? Oh, actually, just 1 crash. Okay? Which one, though? I heard HTC, okay. Is that the only one? Basically, you're telling me that if I everything compiles, but you say that if I try to if I try to cast into HTC, I'm going to have some runtime crash. Is that the only one? Anyone else? This one as well, right? Actually, we'll have two crashes over here, even though they compile. So here's one lesson for you. Even though cast is so appealing to do, you can either do upward casting or downward casting. However, there's a limit. And the limit comes from what the actual dynamic type is. In this particular case, you will run into some some assertion violation, which means this particular part over here. Okay, let me just highlight it quickly. This particular part at a runtime is simply just going to give you false, which means we cannot do such cast. So you write into some check assertion error. If you do this in Java, they will also give you class cast exception. Okay? Similarly, if you try to run this at a runtime, if you try to cast your Samsung into this particular one, that's also going to give you false. Okay? So these two will be. Let me tell you intuitively why it would be the case. Intuitively, that's how you can think of it. Okay? Given that, let me just draw a little bit more picture to show you. Okay? If you think about this is a static type, what type can you cast that into? You can either cast that to here, cast that to here, 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 and here, right? Either upward casting or downward casting. Okay? However, when you talk about any compilable cast, will they write into runtime assertion error? This is what you have to pay attention to. You have to pay more attention to the actual dynamic type yourself, because the compiler doesn't keep track of that for you. Okay? If the type you're trying to cast into is not an ancestor class for the dynamic type, you'll run into trouble. Okay? I'll write it down, and then I'll show you why. So it will be cast error, I'll say runtime error, if the type is not an ancestor of the dynamic type. In this case, you can see this Galaxy model here is not an ancestor class of the dynamic type. And also HTC over here is also not an ancestor for Samsung. Okay? So that's why we run into runtime trouble. So now, can anyone try to justify this for me? Let's focus on one. That'll be enough. Galaxy. So I'm focusing on this particular one. Can anyone give me some intuition about what to justify? Okay? Like how we justify for polymorphism or diamond binding, right? So now, this will actually be some cast error. But now, can anybody tell me why? Given that the static type is Android, dynamic type is Samsung, why can I not cast that into Galaxy S6 Edge? Why can I not? What's the intuition here? This is really good hints. Okay, the hints would be try to justify this using proof by contradiction, which I used for polymorphism. The same reasoning. Anybody want to try before I say it out to you? Anybody else? I would like to point to you, but let's see. You want to try? Go ahead. Side sync?
It's not available in the dynamic type of
In Samsung, right? Exactly. That's exactly right. I'm pretty sure that's what you want to say. Good. Okay, let's see this. This is going to be a class cast exception. Okay. Again, let me just for those of you who haven't followed, for completeness, I'll illustrate very quickly for you. Again, let's say we assume. Okay, I'm talking about this one here, right? We assume the cast was okay. If the cast was okay, that means we do have Galaxy, okay, over here. This is the Galaxy, the new variable, Galaxy, which is the static type of Galaxy is going to be galaxy S6 edge, right, is now going to point to the same Samsung object over here, right? So now, what's the expectation on this particular galaxy variable? What's the expectation? Well, it should be all the way from the root over here, all the way until here, right? Okay, it's going to be dial, surf web, Skype, and also site sync. Agree? Okay. So the expectation over here is, so we do expect to say galaxy dot site sync. So this should be compilable. However, if it's compilable, that means we execute it as an application. So now, if we try to execute this, what's going to happen? Well, the problem is the actual object that's being pointed to is actually a Samsung, which does not support site sync. So we got to write into a crash at the runtime, right? Okay. So this is okay compile, but it's not okay at the runtime because Samsung simply does not support the site sync. I said we're okay. Good. Okay. So again, it's a very quick review on how you do with cast. Either you can do upward casting to really limit the expectation, or you can do downward casting to really widen your expectation. Okay, either way. However, you want to be very careful what you're doing here, because if somehow the way you do the downward casting goes below the actual dynamic type, you're going to run into class cast exception, like in Java. In IFO, it's simply going to be a check assertion error. Okay, the idea is really similar. Are we okay? Okay, good. So we do have a few minutes. I tell you what, I still got a little bit more to be done on Wednesday for sure. But how about we do some very quick exercise here, okay? Very quick. And then you tell me whether that's going to be fine or not. Only a few minutes, okay? Well, I'll let you go in time. What I want you to look at is this particular exercise over here. Okay, everything has been set. Okay, here. Okay, this might be a way to test your knowledge about polymorphism, inheritance, etc. Okay, so now, can you just grab a piece of paper or something, draw the inheritance hierarchy for ABCD over here, and then you tell me this fragment of code, is it going to compile or not? Well, if you're good enough, calculate in your mind. That's okay. That's okay. I don't mind. Okay, but for me, for the purpose of you, I'm gonna draw something. You don't think you will compile? Oh, no, I mean, I just wrote it so we can compare, right? No, not yet. I don't know what I'm doing. Yeah. Okay? Okay, guys, are we okay? So at least, are you okay with, if I give you an inheritance hierarchy like this, can you translate this into something like this? You can, right? Okay, I trust you. Okay? Now, given that, how do we actually do this guy here? Let's say line 1, 2, 3, 4, 5. Are we going to be fine with this? You know what? I'm going to try this. Some magic is going to happen. There we go. It's a trick. Anyway, now, do you think everything's going to compile here? You think it's going to compile or it's not going to compile? Okay, well, actually, there's two different concerns over here. Let's talk about very quickly before I let you go. We'll discuss it a little bit further on Wednesday. Compile or not? Yes, that's fine. Yes, you cannot go. No, tell me which line and then you can go. Line number 4, okay. Line number 4 over here. Can you give me more details over here? Why would it not compile? Basically, whether you want to, if you want to see whether a cast should compile or not, justify by saying whether that should be an upward casting or downward casting, right? It's neither actually, right? Because you can see the static type for B is actually B here. You're trying to cast that into D, nothing to do with B, right? Okay? That wouldn't compile. Now, how can we fix it? Is it possible to fix it using cast? Okay. Basically, you can go through the slides. Basically, what you would do is you can trick the compiler. I can, first of all, cast B to A, and then downward cast A to D. It's going to compile. But does that do you any good? Not really. Because the actual dynamic type is actually C, which has nothing to do with the static type D you cast into. You're still writing into runtime error. Okay. Anyway, details on the slides. Okay, I will see you on Wednesday. Okay.